Hi, my name is Andrew, and I really like to go fishing, and my future goal is to be an engineer.
Hello, my name is Lewis. I like cycling and swimming, and I want to be a neurosurgeon one day.
Hi, my name is Joe. I'm 17 years old, and I would like to pursue a career in the sciences.
Crazy calculus.
Hello, class. Today we're going to be learning some crazy calculus. All right, we're going to get started on our...
Good morning. Yes, Mr. Rubio.
Do you have a pass for me?
No.
I need you to sit down right now. Go get your Inspire. Come on, we have class. Let's go. All right, everybody. First thing we're going to be looking at is... Now, what is this showing? This is showing the value that the function approaches as x approaches a. Now, Andrew, can I get you up here to show me a graphical interpretation of this, just so that all the students can better understand what we're talking about?
As you request.
Thank you, Andrew. All right, class, now we're going to look at a couple of other somewhat special cases, all right? All right, so now if we look at the function as it approaches a, right? So the limit of the function f of x as x, the horizontal value, approaches the value a from the left, we find that equal to b. Yes, Andrew, question?
Mr. Rubio, why do you suck at teaching so much?
The limit of the function as x approaches a from the left is equal to b. Now, Joe, could you come up here and show me what the limit of the function is as x approaches a from the right? If you can read what Joe wrote here, it says the limit of the function f of x as x, the horizontal value, approaches a from the right, so we're going to get this top segment here, is c. Okay? Alright, so continuing our discussion on limits and continuity, Andrew, I want you to come up here and solve this for me. The limit of 3x squared plus x as x approaches 1.
I actually haven't watched this.
So all one would do to solve this problem is plug it in. So the limit as x approaches 1 of 3x squared plus x is equal to 4.
Alright, Andrew, thank you very much for that.
Yeah, you're welcome.
Class,
Mrs. Rubio.
Now if you realize...
Class, just one last thing, just to prove the continuity of a function. So a function is continuous when since the limit as x approaches 1 from both sides is 4, and f of 1 is also equal to 4, then the function is continuous at x equals 1. If any of these were not equal, then the function would not be continuous.
Yay!
Crazy calculus.
Alright, class, so here we have the graph of a parabola, the function f of x. Andrew, could you come up here and draw the f prime of x? Just one tiny thing to point out. The slope of f of x changes from decreasing to increasing at the origin. Your graph doesn't cross the origin. So I am going to fix that, but besides that, you did have the right idea. Now the first derivative is the original, is obviously just the function. This is the point of the function, nothing more, nothing less. That's the information you get, everything. F prime of x is going to show you the slope of this function, right? So wherever f prime of x, if f prime of x, right, is less than 0, like we see right here, right? F prime of x is less than 0. That means that the slope of the original, this means slope of f of x is less than 0. Now if f prime of x is greater than 0, this means that the slope of f of x is also greater than 0. Okay? The other thing that we can get is from f double prime x, the second derivative, wherever the second derivative is positive, so wherever f prime x, double prime x, is greater than 0, f of x is concave up. And if f double prime x is less than 0, then f of x is concave down. The other thing that we can get from f prime x is from the slope. So if f prime x slope is greater than 0, like it is in this case, then that means that the original f of x is concave up. Okay, and then the opposite is true for if the slope is negative. If the slope of f prime x is negative, then the original is concave down. All right, class, one more thing. F prime x, wherever f prime x changes from negative to positive values, it means that, okay, so f prime x changes from negative to positive values. That means that f of x has a relative minimum, and where f prime x changes from positive to negative values, it means that f prime x has a relative maximum. Now we see right here, f prime x changes from negative to positive values, f of x has a relative minimum. F prime x, if there's ever a change in the sign of f prime of x, then we can see inflection points, in other words, change in concavity of the original graph. And if the slope of f prime x changes, we see the same thing. Any change in the slope, yes?
I'm sorry, is that graph f prime of x or f double prime of x?
I'm sorry, this is the graph of f double prime of x. Any changes in the sign of f double prime of x, thank you, Joe, indicate a change in concavity of the original. And then any changes in the slope of f prime of x, and changes in the sign of the slope, so if f prime x goes from increasing to decreasing or decreasing to increasing, it also means a point of inflection, change in concavity of the original graph. First rule that we're going to be covering today is known as the chain rule. So if you have a function, f of x equals a, b, then f prime x, the derivative of f of x, is equal to a prime b plus b prime a. Okay? Now, Joe, I would like you to come up here and solve this. If f of x is equal to 3x times 8 times 8g, okay, what is f prime of x?
So you have a 3x, which means you take the derivative of that. So 3 times 8g plus, then you take the derivative of that one, so 8 times 3x.
Now could you simplify that for me, Joe?
Of course. 24g plus 24x.
Thank you, Joe. Much appreciated. All right, class, today we're going to be learning differentiation by means of power rule. So let's take, for example, f of x equals a to the b. Now f prime x, the derivative of f of x, is equal to b times a raised to the b minus 1. Okay? Andrew, I'm going to ask you to come up here to solve this for me. F of x is equal to 3x to the 4th. What is f prime of x? Andrew? Alright, class, as we can see, Andrew wrote 12x cubed. Now, just to clarify how he got this answer, right? 4 times 3 times x to the 4th minus 1. Alright, then you simplify. 4 times 3 is 12. 4 minus 1 is 3. Great job, Andrew.
Thanks.
Class, today we're going to be learning quotient rule. So what does this mean? If f of x equals a over b, then f prime x is equal to a prime, the derivative of the top, times the bottom, minus b prime, the derivative of the bottom, times the top, over the bottom squared. So Joe, I'm going to ask you to come up here and help us out applying this to the function x squared over x minus 2. Joe, come on up. Thank you, Joe.
Yeah, Joe.
Hi again, class. Andrew is going to come up and explain some applications of differentiation for us.
So, related rates. I'm not gonna get into it because that's kind of hard. And I'm not that advanced as a calculus student. Basically, what related rates is you would have a problem like, let's say you have a cone, right? You know, and it's like filling up. So you would take the formula for the volume of a cone. You would take the derivative of that, and then in there you would use those derivatives to find how the, let's say, volume or height is changing. Next up, we have optimization. And that's basically if you like have a bunch of fencing and you want to make the maximum area possible, that's how you would solve for that. And then linear approximations, which is basically, I need to write it out, you get it. You're making a line to predict a point that you don't have, so you would use the slope, which is the derivative, to find the slope of the line, to therefore find your value.
Crazy calculus.
Hello, class. Today, Andrew here is going to be teaching us a little bit about integration. I'll leave it to it.
This is Andrew's do's and don'ts of integration. So, now we're going to talk about indefinite versus definite integrals. Yeah, so for indefinite integrals, you're going to have your integral, but there's going to be no boundaries. So you won't know from where to where on the graph you'll be taking the integral. So, let's say you have the integral of x squared. You know that the integral of this is x cubed. Let's see, this is when you made the metric. X cubed over 3. But you don't know if there was anything else in there because you don't know the boundary. So it's plus c some constant. Now you have a different integral.
Yeah, I read the whole thing.
You have boundaries. I do, but like A and B. So if you have x squared, and your boundaries are 1 and 2, you can actually get a number. So here's the integral. So you have x cubed over 3.
Yeah, because you want to trade that.
And then you plug in the top number to this and subtract the bottom number. So you have 2 cubed equals 1 cubed over 3. So then, one thing I forgot to mention is that there should be a dx in each of these, which goes away when you take the integral. So when you take the derivative of a function, that is the slope. So the slope is constantly increasing. So the integral is the area under this curve, which will take you from f prime of x back to f of x. So if you have some point A, and you want to take the integral at that point, the area under here is going to be equal to this value up here. So, alright, we're doing a left Riemann sum today, okay? Which is basically going to estimate the area under this curve using 4 different rectangles. Okay? So, basically, to find the different areas of each of these, you're going to use the height times the one on the left, because this is a left Riemann sum. Alright? So, we have the integral here of f of x dx from 1 to 5, that's our boundaries here, so from 1 to 5, is approximately, because this is an estimation, right, this is not the exact number, equal to what we're going to do here. So you have the width times the leftmost height, times 1, plus your next width times this height, so 1 times 3. and so on. Right? So that is the approximation for this graph of f of x.
Crazy calculus.
Differential equations. Class, that's what Joe here is going to be teaching us about today. All right, come up here, Joe. Have fun.
Okay, so this is differential equations. So what you start off with is, let's just say we have dy dx is equal to, and you could pick a random like slope, so x to the fourth y.
Excuse me, Joe?
Yes.
Can you talk louder?
Yes, I can talk louder. So what this means right here is, this is the slope of a function. And what we're gonna do to this is we're gonna basically be working backwards to find what the original function was. So the first step to do this is you're gonna separate. So you see how there's x's and y's? What you wanna do is get them both, like the y's together and the x's together. So you're gonna do dy times 1 over y equals dx x to the fourth. Okay? Wait, pause it. Okay, so then from here, what you want to do is take the integral of both sides. So you set them up in an integral, and then when you take the integral of this side, you'd be left with ln of the natural absolute value of y, which would equal.
Why do you wait?
Yes.
Why do you have to have the absolute value sign?
Because if you get an n negative number in here, then this side wouldn't work because you can't take the natural log of a negative number.
Okay, thank you.
Yes. So
Good job,
you
Joe.
integrate this side.
Yay,
it would be
Joe.
X to the fifth over 5. Now, what you can't forget is you always need to add c. Okay.
Hello again, class. Sorry about that interruption. There was some acid rain in the B wing, so we're back in the A wing. Joe here is going to finish up his lesson. Joe, I'll leave you to it.
Yeah. So as I was saying, now to go to the next step, you want to get rid of the natural log. So you raise both sides to, or you put e as the base of both sides. So then that cancels out and it becomes y equals e to the x to the fifth.
Excuse me, Joe?
Plus c. Yes.
You forgot the absolute value.
Well, now that we know that it can only be positive, so you don't need to put it anymore.
Thank you.
Yep. And now we went from the differential equation back to the original equation, and that's how you solve the differential equation.
Thank you, Joe, so much for this. We're going to call in guest professor Amir Michael to come in and finish up this problem for us.
He will be finding the particular solution.
He will be finding, as Joe found the general solution here, Professor Michael will be finding the particular solution. I'll leave you to it.
All right. Now, we are trying to find the particular solution for this equation at 1, 1. So that means we need to plug in y for one for y and one for x. So the natural log of 1 equals 1 to the fifth, which is the same thing as 1, over 5 plus c. The natural log of 1 is what? 0.
Zero!
Zero!
0 is equal to 1/5 plus c. Because as I just said before, 1 to the power of anything is still 1. So c in this particular solution is negative 1/5. So plugging it back in, we need to isolate for y, which we already have. Not that crazy. So in this particular solution, for 1, 1, y is equal to e to the power of x to the 5 over 5 plus negative 1/5. Thank you.
Crazy calculus.